Hello everyone. Today we are going to study ideal transformer. And in this video, we are going to study what ideal transformer is, relationship between number of turns, current and voltage, and impedance transformation. So let us start. Initially, we'll see what the ideal transformer is. An ideal transformer is a lossless device with an input winding and an output winding. We have already seen what the transformer is. So there is no need to further define a transformer. Now we'll see what are the properties of ideal transformer. No iron and copper losses. No leakage fluxes. A core of infinite magnetic permeability and of infinite electrical resistivity. Flux is confined to the core and winding resistances are negligible. In our earlier video, we have already seen what is transformer and what losses are found in transformer. So in this video, we are studying the ideal transformer. It means that there is minimum or no loss, we can say. Ideal transformer means there won't be any losses occurs. So what is the ideal transformer? It is a lossless device with an input winding and an output winding. So here in this figure, we can observe we have two windings. One is primary one denoted by NP. Another is secondary winding denoted by NS. And current flow through the primary is IP and current flows through the secondary is denoted by IS. So let us see the relationship between the input voltage and output voltage and between the input current and the output current. So we know this equation as Vp at T upon Vs at T is equal to Is by Ip at instantaneous time is equal to A. Okay, A is the constant. This is a well-known equation. Now, if suppose this equation Vp by Vs is equal to Is by Ip is equal to A, where A is the turns ratio, it is constant, and this is for the instantaneous time. And when we talk about the RMS value, the equation can be written as Vp by Vs is equal to Is by Ip, which is equal to A. So to understand this, we have a diagram. In this symbolic diagram, primary winding, secondary winding is shown. Core is shown in between the two windings. Okay. In this diagram, NP is the number of turns on the primary winding. NS is the number of turns on the secondary winding. Then Vp at T is voltage applied to the primary side. Then Vs is the voltage at the secondary side. Ip is current flowing into the primary side. And Is is the current flowing into the secondary side. And A is nothing but the turns ratio. So let us start deriving the equation. So from this equation, we got this equation for RMS value And we are going to use these equations for further derivation. So we know that Vp is equal to Np into d phi m by dt, where Np is the number of turns and d phi by dt, d phi m we had considered as magnetic flux. Similarly, for secondary coil, Vs is equal to Ns into d phi by dt for the secondary coil. And when these two equations we consider, by using these two equations, we can have the equation as Vp by Vs is equal to Np by Ns is equal to A. And from Ampere's law, we can write the equation Np-Ip is equal to Ns-Is. So we are simplifying this equation and the equation becomes Is by Ip is equal to Np by Ns, which is equal to A. But in earlier condition, we know that Np by Ns is nothing but Vp by Vs. So we are simply taking this value and deriving the further step will gives us Vp by Vs is equal to Is by Ip, which is equal to Np by Ns, and which is in turns gives you the number of turns ratio. Okay, so in this way we can derive the number of turns, current and voltage relationship. Now for step-up transformer, Ns is greater than Np and Vs is greater than Vp. So therefore, we can say Is is less than Ip. This conclusion we had drawn from the earlier relationship, what we had derived just now. Similarly, for the step-down transformer, Ns is less than Np and Vs is less than Vp. Therefore, Is is greater than Ip. So what we can say? We can say that for step-up transformer, the current through the secondary coil will be less than that of current through primary coil. Whereas in case of step-down transformer, current through secondary coil will be greater than the current through primary coil. Let's see impedance transformation through a transformer. Here we have a diagram. In this diagram, we can observe two coils are there, and this is the primary coil, this is the secondary coil, and the current through primary, this is current through secondary, and we had impedance load here. So we know that ZL is equal to Vs by Is. We know this very well. So the impedance of the primary circuit can be written as ZL is equal to Vp by Ip. Okay. And this Vp can be written as A into Vs. Since we had the equation, what we had? Vp is equal to, we had the equation, Vp is equal to A into Vs. In derivation, we had seen this. And Ip is equal to Is by A. The two things are taken from the relationship between number of turns, current and voltage. And we have substituted over here. Now when we simplify this equation, we got A square, that is the turns ratio, into Vs by Is. And Vs by Is is nothing but ZL. So we can say that the impedance of the primary circuit can be written as A square into ZL. With this, I stop here. Thank you.